In this video, we will talk about Taylor series. This is our overview slide, which will spend about 5 minutes previewing our video before we go through each topic then in more detail and with examples. Our first topic will be the complex Taylor series, which has the same form as the real Taylor series. And fortunately, even our coefficients are the same. So what we will see, in short, is that the complex Taylor series is just a natural extension of the real Taylor series. The next thing we'll look at is how we can use series expansions of known functions to find representations of other functions. And the 4 different ways we can do this is by replacing z with a simple function of z, something like replacing z with 3z, or replacing z with z minus 1, or z with iz. The second thing we can do is multiply the entire equation by a value. The third and fourth we will not cover at all in this video, but I wanted to put the list there just to make a complete list, which is term by term differentiation, and you treat factors as constants and you leave the summation indices alone, or last you can make adjustments to summation indices. An example is first we find the Taylor series expansion of f of z equals 1 over 1 minus z, and we use these formulas here for the complex Taylor series to get the expansion, and we find it is equal to the summation of z to the n. And this is expanded around z naught equals 0. Then an example of using this expansion here to find representation of another function, we have this example here where the other function is going to be f of z equals 1 over z minus a. Again, we want to find a Taylor series expansion for f of z equals 1 over z minus a using this expansion we've already found, f of z of 1 over 1 minus z. So the trick is we want to use one of these steps, and we're going to use the first step. For the most part, we only use the first 2 steps in this video. We're going to use this first trick to replace z with a simple function of z. So remember, z is a variable. We can replace it with some other function of z. So we want to get this 1 over z minus a into the form 1 over 1 minus z. To do that, we compare these 2 forms. So we have the 1 in the numerator, and that's good. We have a z, that's also good. It could be better if it were a negative z, but it's close. But what we have here is a constant a instead of a 1. So this form is not any constant, it is a 1. So we need to replace this a with a 1. And we can do that if we divide by negative a. So we'll divide the entire denominator by negative a, but that also means we need to divide the numerator by negative a. And that's what we have here. Once we have this form, we're very close, but we need to first because we need a 1 on top, we need to factor out the minus 1 over a, which I've done over here. And now I have minus 1 over a times 1 over 1 minus z over a. And then this is where this step here comes. Replace z with a simple function of z. And so I'm going to replace the z in my known Taylor series. I'm going to replace the z with z over a. So I plug in z over a into my Taylor series, and I get that my Taylor series is going to be my minus 1 over a times z over a raised to the n. And that's how I finish out this example. We'll do it again in detail later in the video. The second important application of using one series expansion to find a series expansion of another is when we did this series expansion here of f of z, we expanded around z equals 0, z naught equals 0. So here, when we did obtain our Taylor series for f of z equals 1 over z minus a, this was an expansion around z equals 0 because we had leveraged this other expansion around z equals 0. But what if we want to expand around z equals z naught? So again, looking at our function, so this is the same example, f of z equals 1 over z minus a. I'm going to introduce a z minus z naught term in here, or factor in here, and I just subtract z naught from my z. But of course, since I subtracted a z naught in my denominator, I need to add back a z naught in my denominator, and I do that by subtracting z naught from A. And because of this negative sign, it's like adding a z naught. So this is algebraically equivalent to this. And now I'm back at the point where z minus z naught can substitute for z in my known Taylor series. But now I have my A minus z naught instead of my 1. It's the same problem I had in this previous example here when I was expanding around 0. So I can divide everything now by A minus z naught, which I've done here. And then I can plug this in for z into my series expansion, and we'll finish off and do this problem in detail later in the video. But now let's wrap up our overview and let's go back and talk about complex Taylor series. The general form of the complex Taylor series looks just like the real Taylor series. It's a polynomial here, so we have a coefficient, another coefficient times z minus z naught raised to the first, coefficient z minus z naught raised to the second power, and on up to the nth power. And the z naught here, this is where our Taylor series is centered, and so it's where our approximation is best. As we move away from z naught, our approximation isn't as good. But here we have an infinite series, and if our Taylor series converges, then we will have not just an approximation, but an exact approximation. We can derive the formula for Taylor series coefficients by selecting an expansion point z naught and a counterclockwise circular contour C centered around the expansion point. And I'm just going to outline a few points about the derivation of this formula without actually deriving the formula. Your book outlines the derivation more, but I don't want to focus on the derivation in this video because there are more important techniques we need to get to. But there are some things worth mentioning. So assuming f of z is analytic everywhere inside C, then we can use Cauchy's integral formula. Here is the Cauchy integral formula we're used to seeing. F of z naught is equal to 1 over 2 pi I, integral over C, f of z over z minus z naught dz, where z naught is inside C. So in this formula, we were looking at z naught anywhere inside C. In this chapter, we're considering z naught, because it's our complex Taylor series, as the center of our Taylor series, also the center of our circle. So we need another variable for z naught, and in this chapter in your book, instead of z naught, we use z, which means this z here needs a different notation, so we use z prime. So z prime is not the derivative, but it's the complex variable of integration that lies along C. So it basically replaces this z here in the formula. So that was very belabored, but after some calculation with this form, and this is where I'm just going to avoid doing all the derivation, we do get that Cn is equal to, and Cn again is our coefficient, is equal to 1 over 2 pi I integral over C dz prime f of z prime, and remember z prime is the variable of integration, z prime minus z naught n plus 1. So what that gives us is 1 over n factorial, the nth derivative of f of z evaluated at z naught. And this should look familiar to you because it's the same coefficients we used in the real Taylor series. So the complex series coefficient is a straightforward extension of the coefficients for the real Taylor series. And these coefficients will generate a complex Taylor series that will converge to f of z for all z inside C. So our first example of a complex Taylor series, we're going to obtain the Taylor series expansion for f of z equals 1 over z minus a. And first, this function is analytic everywhere except at z equals a, where we would have division by 0. To avoid a, we're going to expand around z equals z naught, and we're going to make C a circular path centered at z naught with radius such that 1 over z minus a is analytic. That is, we want z prime, wherever we are on the circle, minus z naught to be less than a minus z naught. So in other words, C, the radius of our curve, our contour C, is going to be smaller than the distance from Z0 to A. So you can just kind of see this picture. We're going to stay, our curve and everything else is going to stay in the analytic region and be small enough to avoid our point A. Since the coefficients all need derivatives, I started by taking derivatives. I rewrote my f of z equals 1 over z minus a as f of z equals z minus a to the negative 1. When I take my first derivative, I'm going to have my negative 1 z minus a to the minus 2. My second derivative is going to be my negative 2 times negative, this negative here will give me 2, z minus a to the third derivative, f triple prime. Now I'm going to have, in this case, I started seeing the pattern. I'm going to alternate my negative sign. Then I'm going to have 3 times 2, which is 3 factorial, because it's 3 times 2 times 1, z minus a to the minus 4. Plugging these derivatives into my formula for my coefficient, so my 0th coefficient is 1 over 0 factorial times my 0th derivative evaluated at z equals z0. So where's my 0? That's my actual function over here. So that's going to be 1 over z0 minus a. My first coefficient is going to be 1 over 1 factorial times my first derivative evaluated at z equals z0. So that's over here. My first derivative evaluated at z equals z0 will give me my z0 minus a squared. Then my second coefficient over here is 1 over 2 factorial, and now times my second derivative, so that's 2 over z0 minus a cubed, and then I have my c3 over here. And now that I have my coefficients, I can plug in to this formula here. So I have c0, which is my minus, 1 over 0 factorial is 1, so minus 1 over a minus z0. For some reason I put this back in this form, in this order, plus c1 is over here, my 1 over z0 minus a squared, z minus z0, plus my c2 times z minus z0 squared, plus my c3, times z minus z0 cubed. So what I get is n equals 0 to infinity minus 1 over a minus z0 n plus 1 times z minus z0 to the n. And one thing to remember, this series converges everywhere inside the circle of radius a. So not on the circle, but inside the circle of radius a, centered at z equals 0. And the circle is called the singularity circle, and it's the largest radius that the contour C can have while still keeping f of z analytic everywhere inside. Now that we have the formula for this Taylor series, we're going to do more examples of Taylor series, but we're going to use it along with the second point, which is that we can use series expansions of known functions to find representations of other functions. And we're going to start by expanding f of z equals 1 over z into a Taylor series. And here, because z equals 1 is where we are not analytic, we're going to have our circle be less than 1. We are going to center our Taylor series expansion around z equals 0. So now f of z equals 1 over z, so f at 0, because we're expanding around 0, 0 is our center, is equal to 1, which means that c0, here's our formula here for c0, is 1 over 0 factorial times our 0th derivative, which is just our function evaluated at z0, so that's 1, which is equal to 1. Our first derivative of this function now is 1 over 1 minus z squared. So the first derivative evaluated at 0 is also going to be 1. So c1 is now 1 over 1 factorial, which is just 1, times the first derivative of f evaluated at z0, which is 1, so we still get 1. F double prime is a little more interesting. We have 2 over 1 minus z cubed, and then evaluated at 0, this is equal to 2. So c2 over here is 1 over 2 factorial times our f double prime at 2, which is 2, so we get 1 again. And as you might have started to guess, when you do the triple prime, this is what you get, 2 times 3, and I could have rearranged this as 3 times 2, so it looks like a factorial going on top, 1 minus z to the 4th, so f triple prime at 0 is 3 times 2, so c3 is 1 over 3 factorial times 3 factorial, which gives us the 1. So what that gives us is f of z equals 1 over 1 minus z equals our c naught, which is 1, plus c1 times z minus z naught, which is 0, so z minus 0, plus c2, which is 1, times z minus 0 squared, plus 1 times z minus z naught cubed. So we have this function is equal to 1 plus z squared up to zn, or in other words, the summation from n equals 0 to infinity, z to the n. So I have this written up here as my solution. So this is one of the, I don't know, the simple kind of, I guess this series is a simple series, and often it is used as kind of the basis for trying to find the Taylor series of other more complicated functions. So we're going to do an example of this, but this is an important series, and you might want to remember that this f of 1 over 1 minus z is equal to the series z to the n. Two more quick notes. One, we want to remember that we got this function by expanding around x naught equals 0. Second, we can also verify convergence using the ratio test. So if we take the limit of our nth plus 1 term over our nth term, we get absolute value of z. And remember, we had set our radius, our singularity circle, to be absolute value z is less than 1. So this is less than 1, and this series does converge absolutely in this range. So as I said, we're going to now use this Taylor series expansion to reconsider our last example when we had looked at the Taylor series expansion of f of z equals 1 over z minus a. And we calculated this, the Taylor series expansion, by using this formula for the coefficients, and we got this answer here. But let's compare this with this second technique. And we're going to expand the f of z equals 1 over z minus a around z naught equals 0, and that's important because that's what we calculated this Taylor series expansion of f of z equals 1 over 1 minus z around. We calculated around 0. So if I want to use this formula here, my 1 over 1 minus z equals the summation from n equals 0 to infinity z to the n, I need to put my f of z equals 1 over z minus a into this form. To convert this now 1 over z minus a into the form 1 over 1 minus z, actually I'm going to compare it to this up here. So the 1 in the numerator, that's good. The z looks pretty good. And then the problem I have is this is not just some arbitrary constant minus z, it is 1 minus z. And over here, I have an arbitrary constant a. But I can make this a into a 1 by dividing by a. And even better, I want a positive 1, so I can divide by negative a. So I'm going to divide both the denominator and the numerator by negative a. So that's exactly what I did here. I have 1 divided by negative a now in the numerator, and in the denominator I'm going to have minus z over a plus 1, and that gets us into this form here. It doesn't quite look like that, so let me do a couple of more things. Oh, here's my form. I'm going to factor out my minus 1 over a so that the top becomes a 1. And then I still have the bottom, and now I have 1 minus z over a. And this is a fine form. This is exactly the form we want, the 1 over 1 minus z, because according to the steps we can take, we can replace this z with a simple function of z. And the simple function of z that we're going to replace the z is z divided by a. So I kind of tried to note this with the z minus a replaces z in this formula. And now I can use this series expansion for 1 over 1 minus z, but instead of z over here, I'm going to be plugging in z over a. So now I'm going to have 1, z over a, z over a squared, z over a cubed. So this is looking good, but don't forget, this expansion here is just for the 1 over 1 minus z over a. I still need to multiply by negative 1 over a. So f of z is negative 1 over a times the expansion I just have over here. Then from there, I just multiply through, and I finally get that f of z is equal to n equals 0 to infinity minus 1 over a n plus 1 to the zn. So this is our answer. And if we compare it to the previous answer we got when we worked out the Taylor series, you see it doesn't quite look the same, but it's close. The difference is here we centered around z naught equals 0. So if you plug in z naught equals 0 into this formula, you will see that our two answers match exactly. So we will talk about in just a minute how we can then take this form, or the work we've done here, and then look at how we would expand around z naught next. For now, we just know how to expand around z equals 0 because we're using this formula here. First, we just want to confirm convergence. So we use our ratio test. So the limit as n approaches 0 of a to the n plus 1 over a to the n. And I should say our nth plus 1 term over our nth term. So I'm going to have minus 1 over a n plus 2, because I'm looking at our n plus 1 term, z to the n plus 1. Then our nth term is minus 1 over a n plus 1 z to the n, which is equal to minus 1 over a times z, which is equal to z, or the absolute value is equal to z over a, which is less than a, because remember, we're inside this circle here, our singularity circle. So the distance z to z naught, and in this case z naught is equal to 0, is less than the distance from a to 0. So here we have shown we have absolute convergence according to our ratio test. Now we're going to go back to that little detail when we derived this formula. We expanded around z equals 0, but what if we really want to expand around z equals z naught? So we're going to look at our function again, our f of z equals 1 over z minus a. And we want it in this form. We want some sort of expansion, a polynomial expansion, but we want z naught to be our center as opposed to just 0. So in order to get this z naught, I need to introduce z naught into my function f of z. And now I can introduce that just simply by subtracting z naught from my z. That's exactly the form that I want. But of course, since now I've subtracted a z naught in the denominator, I need to add back a z naught. So for this term, the minus, for the a, I'm going to add a minus z naught. So this is how I add back in my z naught so that these two are still algebraically equivalent. Now comparing this to my form of 1 over 1 minus z, remember this z can be replaced with a simple function of z. So z minus, remember z naught's a constant. We know what we're going to center at. Eventually we know what we're going to center at, but z naught represents a constant. So this z minus z naught is a simple function of z that we can replace this z with. But over here we need a 1, not this constant here, a minus z naught. And remember, this is just a constant too. A is a constant, z naught is a constant. Now this becomes exactly the same thing we had when we were trying to write f of z 1 over z minus a to look like 1 over 1 minus z. What we did is we divided the entire numerator and denominator by minus a to make this minus a 1. So now over here, we're going to divide the entire numerator and denominator by negative a minus z naught, and that will give us a 1 in this position here. You can see here I've divided the numerator by minus a minus z naught, And then in the denominator, z minus z naught divided by negative a minus z naught. And then when I divide a minus z naught by negative a minus z naught, I get my positive 1. So this should be familiar to you from this example. So this is a common technique. So not only should it be familiar, but you should memorize, or you should remember it. So now I'm going to factor out my constant on top so that I get the form 1 over 1 minus, and then a function, a simple function of z. When I plug in my z minus z naught, a minus z naught, this constant here, I'm going to replace the z over here, and I'm going to put it into this formula. And also first over here, I'm going to make sure I keep my term 1, my constant term, minus 1, a minus z naught. And then I'm going to plug this in for z in this formula. So I'm going to get 1 plus z minus z naught over a minus z naught plus z minus z naught, a minus z naught squared, etc. Now when I multiply my a minus z naught in the denominator through by all of these other fractions over here, or all the other terms, I'm going to get the summation as n goes from 0 to infinity minus 1 over a minus z naught to the n plus 1 times z minus z naught to the n, which now matches the same formula we had when we calculated this directly from our Taylor series formulas here for the coefficients. And that's this example here. So again, we had a series that was expanded around 0, and then we kind of manipulated our series so that we could use this formula even though we were expanding around z naught. So that's the second way we can use a series expansion, a known series expansion, to find other representations. So this technique here, after a while, becomes really important. You're going to use it a lot. So the way you're going to find new Taylor series and Laurent series expansions is by knowing a few key series expansions of known functions, and your book gives you this one. So I would know it, I would memorize it, and then from there you kind of derive other Taylor series expansions of other functions. But this is one you need to remember. F of z equals 1 over 1 minus z is the summation of z to the n. I'm going to give you another example. So here is our known Taylor series, which, by the way, I just realized this has x's in it all of a sudden. I don't know why. I'm going to go back and fix it. So maybe by the time you see this video, you'll see z's over here. But anyway, using this Taylor series expansion, we want to obtain the Taylor series for f of z equals 1 plus 2z squared over z cubed plus z to the fifth. I am going to mention, if you are time constrained, for example, on an exam, I would probably give you 1 plus 2z squared over z cubed plus z to the fifth is equal to 1 over z cubed times 2 minus 1 over 1 plus z squared. However, I think it's important that you understand the reasoning to get us to this this function here. And also you can see, because of the 1 plus 1 over z squared is exactly in the form we want, right? This z is just replaced by a simple function of z. The first thing I would note is in our known Taylor series expansion here, z is just to the first power. There are no other powers of z. So the first thing I would do is here in the numerator, I would get rid of the z cubed. Well, I don't get rid of it, but I'm going to factor it out. So what I am going to get, my f of z equals 1 plus 2z squared z cubed plus z to the fifth is equal to 1 over z to the third times 1 plus 2z squared. And then factoring out the z cubed, I have 1 plus z squared. Now looking at what I have, I'm going to multiply my final series by 1 over z cubed. And over here, I have what I want to eventually be in the form of 1 over 1 minus some small function of z. So the bottom's looking good. The denominator, 1 plus z squared, here my small function of z is negative z squared. That's great. And the 1 over here is great too, but what I have is this 2z squared, which is giving me problems. So there are many ways algebraically you could get rid of this 2z squared, but what I chose is to see that this form here, what's in the numerator, looks very similar to the denominator. In fact, what I see is if this were a 2, so I'm going to make it a 2, and then I'm going to subtract a 1 to keep it algebraically equivalent. But since this is now a 2, this here is a multiple of what's in the denominator. So in other words, I pull out a 2, and I get 1 plus z squared over 1 plus z squared in the denominator, and I also have my minus 1. Canceling over here, now you can see how we get 1 over z cubed, 2 minus 1 over 1 plus z squared. So that's just to get us to this algebraic equivalence. And of course, you might have done some other algebraic steps, but eventually you want to get something in this form. And now on this 1 over 1 plus z squared, I can expand using this formula here. My f of z equals 1 over 1 minus z is equal to summation z to the n. I've kept my 1 over z cubed, I kept my 2, and now for this 1 over 1 plus z squared, I'm going to substitute z squared in this Taylor series expansion in for z. So I'm going to get summation n equals 0 to infinity minus z squared to the n. And I kind of notated what I replaced here in blue. I did a little bit of algebra, separating out the negative, and then I have my z squared to the n is just z to the 2n. And now I'm just going to expand out my summation, so plugging in n equals 0. So I'm going to get z to the 0, and then n equals 1, so I'll have a negative, then z squared. N equals 2, I'll have a positive z to the 4th. Working out some of this, I have my z to the 0, I just plug in my 1, and then I divide everything by z cubed. So my 2 minus 1 gives me 1, so I have 1 over z cubed. I have my z squared over z cubed gives me 1 over z. My minus z to the 4th over z cubed gives me a minus z, and then I keep going from there. So I'm going to tell you, this is a good place to stop, but I wanted to give you one more example, but it's like a super bonus example. So if you've had enough, I would say you can stop. But if you get to your homework and realize you need more, come back and look at this last example. So it's an example here. We're going to do another complex Taylor series, and then we're going to use this series that we have to find another representation. So we're given a function f of z equals e to the z, and we're going to find the MacLauren series, and a MacLauren series is just a Taylor series centered at z equals 0, representation at z equals 0. So f of z is given to us by e to the z, and then because our coefficients need the derivatives, I'm just going to take a bunch of derivatives. So f prime of z is still equal to f of z. In fact, fn to the z is equal to e to the z. So fn at 0, since we're centering at 0, is equal to e to the 0 is equal to 1. So now our Taylor series expansion, we have f at our 1 over n factorial, 0 factorial is 0, and then our 0th derivative is just our function evaluated at z naught, plus our our 1 over 1 factorial f prime at z naught times z minus z naught. So because now we have f, not just the coefficient. And then f double prime of z naught over 2 factorial z minus z naught squared, f3 triple prime z naught over 3 factorial z minus z naught cubed. So here, all our coefficients are equal to 1. So we have 1 over here, and z minus z naught to the 0 is 1. Here we have 1 over 1, and then we have z, since z naught is equal to 0. We have 1 over 2 factorial, z minus z naught is z squared, 1 over 3 factorial, z cubed, up to 1 over n factorial, z to the n. So this f of z equals e to the z is the summation from n equals 0, z to the n over n factorial. We are now going to use this Taylor series expansion of e to the z, which is the summation of 1 over n factorial z to the n, to find a MacLauren series. Remember, MacLauren series is just a Taylor series centered at 0 of f of z equals sine of z. The other thing we're going to use is this formula here that we had introduced a few videos ago. So depending on how much your teacher likes to use this formula, this may or may not be something worth memorizing. But anyway, sine of z is equal to e to the iz minus e to the minus iz over 2I. So we're going to use this form of sine to get a MacLauren series expansion of f of z equals sine z. So we start with sine z equals 1 over 2I, so I factored out the 1 over 2I. E to the iz minus e to the minus iz, again, that's given to us. And now, this is fairly straightforward. I have e to the iz, and this is e to the z. So remember, I can replace my z with a simple function such as iz. So I'm going to plug in iz here. So this first term here becomes 1 over n factorial times iz to the n. And then the second term here, I just plug in minus iz for zn. So again, I get 1 over n factorial minus iz to the n. And this is it. The rest of this is just algebra so that I can convert this into a form that's our familiar sine of z. But the main idea is right here. If you are interested, I'll just leave this algebra here. And that is my last example. What we have covered in this video is we looked at the complex Taylor series. First, we looked at the formula for the complex Taylor series, which is totally analogous to a real Taylor series. And we found that we could use Cauchy's integration formula to calculate the coefficients of our Taylor series, but then we also found that it's exactly equal to the same formula that we had for real Taylor series. So that was nice. So basically the complex Taylor series is just an extension of the real Taylor series. Next, we did some examples of complex Taylor series, and in particular we did this example here, which is an important example because it's one of the basic Taylor series expansions that people know, and then they can use some of these known series expansions to find representations of other functions, and that's what we did for the rest of the video. We did examples of these first two techniques. The first one was replacing z with a simple function of z, something like 3z or z minus 1 or iz. And the second is by multiplying the entire equation by a value. We did something like that. We factored out a 1 over 3z somewhere, or no, 1 over z cubed. So that was sort of the same sort of idea. We did not do examples of the next two techniques, term-by-term differentiation or make adjustments to summation indices. Term-by-term differentiation, you might use it if you have something like a sine series and you want to do something with a cosine series, just differentiate each term, each thing separated by a plus sign. Make adjustments to a summation indices. We also did not do those examples. We didn't do these because they weren't in your book, and so I wasn't sure if you'll be using that in your book later, but I also wanted to make sure that you at least know about these in case you run into something in the future. So once we had a couple of Taylor series expansions, we used it again to find representations of other functions. And our first example was f of z equals 1 over z minus a. To get it in this form, we have a z, but we didn't want an a, we wanted a 1. So we divided everything, the numerator and the denominator, by a. So you can see that over here. And then we can factor out this minus 1 over a, and we get 1 over 1 minus z over a, which is exactly this form. We just substitute z over a for z now, and then you can see that we were able to work and finish out that problem. The second important type of problem we had is we had this function here which was expanded about z equals 0, and we want the related equation, we want to be able to expand about a random z naught. And so what we did is to f of z equals 1 over z minus a. We introduced z naught, so we have z minus z naught. So that's exactly the form we want. But of course, in order to add or subtract a z naught, we need to add a z naught. And that's what we did here. And then from there, we did our manipulations, our algebraic manipulations, so we could plug it into this form, 1 over z minus a. And you can see that here. So that was it for this video. It seems like a lot. I feel like this is a hard thing to get until you have some practice. It starts to become more natural. This part here, not plugging into the Taylor series formula, but this stuff here becomes more natural with practice after you've done a few examples. Anyway, that's it for this video. Thank you for watching.